The dot product is a way to multiply two vectors. And whenever we multiply two vectors using the dot product, the product is actually going to be a scalar. So the product is just going to be a number. We're going to do some examples. Like if my vector u is 1, 2, and my vector v is negative 1, 3, like this, then whenever I have u dot v, I'm going to take the first two entries and multiply them. So I'm going to have 1 times negative 1. And then I'm going to take the second two entries and multiply those. 2 times 3. And then I'm going to add those together. Just take the sum. So that would be negative 1 plus 6, and that would be 5. So here, in that first example, 5 is the dot product of u and v. So just like I promised, the dot product is a way to take two vectors and you're multiplying the vectors, but the product is actually a scalar, like 5. Your vectors do have to have the same dimension if you want to take a dot product, right? If you want to multiply two vectors like this, they have to have the same number of entries. So the second example. If I want to take the vector u to be 4, 5, 6, and the vector v as negative 1, 0, 2, then u dot v, that's going to be 4 times negative 1, which is negative 4, plus 5 times 0, which is 0, and then 6 times 2 is 12, and you add all those up and we get 8. So 8 is the dot product of u and v in that second example. Does this make sense? Okay, this should be an easy operation to memorize. Okay, one more, and we'll move on. So if I have this as u, 4, 3, 2, 1, and then the vector v is negative 1, 0, 10, 1, then u dot v is going to be 4 times negative 1 plus 3 times 0 plus 2 times 10 plus 1 times 1. So that will be 17. Okay, so you can probably figure these out, but the dot product has these properties. Number one, we call this the commutative property. Commutative property just means you can swap the order of your vectors, and it doesn't matter, right? Because we're just multiplying them element-wise and then adding it all up. It has the distributive property, just like ordinary multiplication of numbers has the distributive property. It has the associative property, same thing. By the way, whenever it's talking about the associative property, that c is just a scalar, right? So if you want to multiply by 2, c is a scalar there. if we're here where it says 0.u equals 0, that 0 means the 0 vector. So whatever the dimension of u is, just that many zeros in the list. Obviously, multiplying every entry by 0 and then adding them up is going to be 0. And you'll notice what we did for the norm of a vector, like if I take the norm of u, and let's say that u is the vector 1, 2. The norm of u is just the square root of 1 squared plus 2 squared, right? And so if I did u dot u, that would be 1 times 1 plus 2 times 2, because I'm dotting the vector with itself. So that would be 1 squared plus 2 squared. So that would actually be just the norm squared, okay? So that's what I mean over here whenever I say that, if you dot a vector with itself, that's just the same thing as the norm squared. Does that make sense? Okay. Another way you could write that, the same idea, is you could say that the norm of a vector is equal to the square root of that vector dot itself. Okay. I'm going to skip that, because I think that's pretty straightforward. Since we're short on time, I'm going to skip the proof. Maybe I can get back to it on Monday. But this is one thing that you ought to remember, and I only ever saw this in like 10th grade geometry class, and then I didn't see it again until Calculus 3. And so maybe we've forgotten this, but this is called the law of cosines. And for any triangle, we could label the sides of the triangle A, B, and C for the side lengths. And if we did, we could label the angles, say alpha, beta, gamma. And really the only important thing here is that this gamma is the angle across from C. But this is a lot like the Pythagorean theorem, but it's sort of a generalization of the Pythagorean theorem. To use the Pythagorean theorem, that angle, gamma, has to be 90 degrees. And if the angle gamma is 90 degrees, then cosine of 90 degrees would be 0. And so that last term would go away and you would have the Pythagorean theorem. But if you don't have a right triangle, there's no angles that are 90 degrees, then this law of cosine still works for any triangle. So go ahead and write this in your notes and have it ready to use. Like I said, there's kind of a neat proof for the law of cosines, but I'm going to skip it for now because we only have 2 minutes left. Then this formula is going to be really, really important as you try to work your homework for section 11.3. And this formula is one that you really, really need to have memorized for like your exam next week, and for every exam and for the final exam. Okay, so make sure you have at least one of these memorized. Your textbook only shows you the middle version, but you absolutely must memorize this. Where it says cosine theta is equal to u dot v, all divided by the norm of u times the norm of v. The theta there is going to be the angle between the vectors. So like, if this vector is u, This vector is v, and this angle here is theta.